All right, thanks for having me back for a third time and the final time. Today, I'm going to give a slightly longer talk, a deep dive into the scientific computing, research and development, engineering, and practice. And so we'll get into what that means in a second. But basically, what I did for this talk is I kind of took the project, the quantum AI and climate project, and kind of went through it myself actually over the past couple of weeks here. And turned it into sort of how I would approach this problem, and a little bit of sort of the thought processes I went through when going through the project in sort of my context, and then giving you a little bit of additional background into sort of like what are the thought processes involved when doing this type of R&D in general. So I'm going to give a quick introduction to what is this R&D engineering field that I keep referring to and I refer to myself as. And then go into this case study with the project, right? So for my iteration of this project, I chose radiative transfer through the cloudy atmosphere, which is something that comes up quite a lot in the atmospheric modeling community. And so I'll go into a little bit of what are some of the at a very high level, what are some of the methods and the background involved in doing that, how it's solved and programmed today, and then ultimately answering the question of how do things like AI and quantum affect this type of calculation and how could you use to accelerate them. And then we'll go into discussion. And so I've got two discussion breaks in this talk. So we'll take one about halfway through because the first material is going to be kind of dense. So we'll give everybody a break in the middle to get a chance to ask questions, get up, get a drink of water, what have you. And then we'll move on to the latter half of the talk, and then we'll have questions again at the end. So that way we can move kind of slowly. We get lots of time for discussion and get everybody's questions answered. Before we begin, obviously the caveat here, I'm an engineer, not an atmospheric scientist, and I figure most people in the audience are not either. So I'm going to try and keep the discussion qualitative. Some of the math involved with these types of calculations is very beautiful, but it's very complex, and I don't want to either put people to sleep or scare people away with sort of the complexity that's involved here. So I'm going to try and be clear in my description of things rather than trying to be precise. So if there is somebody in the audience that's an expert, there's probably a better, more precise way of describing something, but I'm just trying to be clear to everybody so that we can all follow along together. And finally, I'm going to try and respect the complexity of the domain. Obviously, like I said, I'm not an atmospheric scientist, and nobody likes an outsider coming in and telling them how to do their job or trivializing what they do. So I'm going to try and be respectful that there's a lot more complexity involved in what I'm showing here today, and that's something that you have to take into account when really developing any kind of product, whether it's a software product, a new method, or even a new physical piece of hardware. So what is R&D engineering? This is sort of like how I refer to myself, even though it's not my official job title, but what it really is you try to build something new and useful once sort of the basic science is done, right? So not necessarily starting from complete scratch and coming up with a brand new theory or what have you, but really after that initial work has been done, now you want to take that and show that it's viable in either a prototype context or taking a prototype and then turning it into that first run of a product. So you want to basically show your users, your stakeholders, that you can build a stable prototype of a product that you can then build upon and scale. So one way of thinking about this would be like chemical production, right? So you could do a benchtop experiment showing that it is possible to make a particular type of whether it's a food product or soap or any type or drug or any type of chemical, you can do it on the benchtop. But then you need to show, okay, well, we're not really making it in the laboratory, we're making it in a big factory. So then your next step would be to make a pilot plant. This is kind of the realm that I work in here, is taking that benchtop experiment and turning it into a pilot of what this might look like in production. And then finally, when after you've proven it on the pilot scale, that's when you scale it up to the full production scale when you've got these giant things. And then that takes a much larger team of people and much more dedicated resources to do that. But the goal is to try and prove or disprove that you can do a job better with a new technology. Because ultimately, whenever there's a new technology out there, there's lots of hype, there's lots of excitement, but ultimately you want to get a job done. So you want to take that and show that you can actually get that job done. So what does that look like in scientific computing then? So in this case, we're basically doing simulations. So in this case, you want to say, there's a new method, a new algorithm, a new computer architecture that has some theoretical or claimed benefit. AI is one of those things. Quantum is one of those things. So, okay, now we want to make it concrete. We want to confirm or refute those results in the real world to say, okay, is quantum going to be useful for my use case? Is AI going to be useful for my use case? And it doesn't match the use case. So you want to basically confirm or refute those results as well as verify that it matches what you're trying to do. That's sometimes called a technology push, right? So there's a new technology and you want to push it out to your community of users and stakeholders. Then there's the other side of that. Your users, your customers, your clients, they have or need a new capability and they want to know what's out there that can get this job done the best way, most efficient way possible. That's when you work with them to try and match, okay, what's the state of the art right now that we can tailor to this job? So scientific computing in practice. And I showed this slide in the talk I gave a few weeks ago, but basically the workflow looks kind of like this. The first thing you have to do is you have to ask a question. So what am I trying to simulate? Is it a space shuttle? Is it a hurricane? Is it a car? You have to understand what is it that you're trying to do. And then you have to model the problem. So you come up with some mathematical description of what that problem looks like. Then you have to take that and actually map it into something that runs on a computer, whether that's a classical computer, whether it's a GPU, whether it's a quantum computer. You have to basically come up with, okay, how do I translate this set of equations into a computer program? Then you have to solve the problem. So then you run it on whatever computing resources that you have, and then you get some answer out. How do you know that answer is right? You have to basically go through a whole bunch of testing, validation, verification in order to actually have confidence that your answer is going to inform real world decisions that have to be made with it, sometimes with fairly high stakes. So there's a very rigorous verification and validation process that has to be done. And then finally, you have to report your findings. Generally, the person developing the code isn't always the final user, especially in sort of the engineering field. So you have to communicate to the people who are going to be using it, why they should care and why this is an important way of getting the job done. Now, in the context of the project, we set out to ask, okay, why was the problem we picked important? So why did we pick it? And then we want to say, how is this problem currently solved today? So when I get into the topic I chose, I'll spend a decent amount of time explaining that. And then we want to answer the question, how does quantum computing or AI improve the way that this problem is solved? So these new technologies that are out there that there's a lot of excitement about, how does this actually make my life better? We want to answer that question. And then finally, when it comes to now taking this existing work that I have and implementing the new technology, whether it's AI or quantum, how do I go and do that? So these are the questions that we want to answer for the project, and I will try my best to answer those today. I have a little bit less time than the folks in the audience had doing this project, so it's going to be a little bit less detailed, but hopefully it should give you a flavor and a little bit of inspiration of what you might want to go after when doing the project. Okay, so the problem is the solar radiation energy transfer. So what is that? So when you think about the Earth, basically all of the energy it gets, all of the energy balance that both energy in and energy out occurs through radiative transfer with space. So you have incoming light from the sun. It's absorbed by the Earth and the atmosphere. And some of it is re-radiated back to space. Some of it is trapped by the atmosphere. Some of it is absorbed by the land. So either way, there is this whole energy in, energy out balance that has to be calculated. Because ultimately that drives basically all the weather and climate phenomena that we care about. The caveat here is that there's right now in the atmospheric modeling community, a major source of uncertainty in trying to simulate all of this are the clouds, radiative transfer through clouds. There's many different kinds of clouds. There's many different layers and strata involved in them. And so understanding how light and infrared and electromagnetic radiation interacts with clouds is a major source of uncertainty in weather and climate simulations. And to add to that, actually simulating this radiation transport through the atmosphere is very computationally expensive. So you can't just run a million radiative transfer calculations. You have to be smart about how you do it. It's probably one of the most expensive governing equations that regularly gets solved, and I'll get into a little bit as to why that is. So the question we want to answer then, can AI or quantum computing contribute to improved answers in atmospheric radiation modeling? And what kind of research have people done to this area in this area to date? So I'll hopefully try and set out to answer those questions. It turns out AI has been around a lot longer, and so a lot more people have been trying this. Quantum is still fairly new and still fairly unfamiliar to people, so there's a little bit less out there in terms of this, but I'll try and cover a little bit of, the ground that has been covered. All right, so modeling the problem. So a very oversimplified picture of how radiation moves through the atmosphere can sort of be looked at like this. You basically divide it into layers of planes. So you have this top of the atmosphere. So somewhere in space, you call that is the top of the atmosphere. So light is just coming in at that boundary, because we don't really care about what's going on way out in space. It's too far away. It doesn't really affect too much on Earth compared to these lower altitude interactions. So when you have light coming in, you can do a variety of things. This is not exhaustive, but you can have absorption by atmospheric gases, so water vapor, CO2. You can have light traveling all the way through the air and being absorbed at the surface. You can have clouds that reflect light back to space. You can have light traveling through the clouds, scattering around, and then making it down to the surface again. You can have scattering off of atmospheric gases back to space. You can have absorption by aerosols and other human-contributed constituents of the atmosphere. And this is just the input side, right? There's also the whole output side where, okay, now you have infrared radiation being radiated back to space, which can be trapped by gases. It can be reflected down to the surface, and a whole number of different things could happen. So we need to fully account for all these different processes that are occurring when modeling this behavior. And so in general, when we want to model these scientific processes on a computer, the first place we start is the math. And the math that underlies basically all physical phenomenon are partial differential equations, or PDEs. So these are basically differential equations that have a multidimensional spatial component, sometimes a time component, but ultimately they have this differential component to them that comes into play because everything is dynamic and changing. But in general, PDEs do not have analytical solutions. So you can't just use regular algebra and calculus to get a solution. There are some very limited exceptions to that for simplified problems, but in general, you need numerical methods. So some common PDEs that we encounter in our everyday life, Navier-Stokes describes how fluids flow. So whether it's a tornado like this one here or water in a river, that's all Navier-Stokes equations. And in fact, I remember being, when I was a kid, wading through a river like this, and I think I had just taken calculus at that point. I was like, man, I wonder what the math is behind, all this cool looking rapids and stuff in this river. Well, here it is, Navier-Stokes equations. Other ones we might be familiar with, the heat equation. So this is actually one of the more simple PDEs that we can solve. You just think of this metal bar here heated on one end. And then after you've taken the heat source away, this hot end, the heat will diffuse to the cold end, and so it'll sort of equilibrate. And so the heat equation describes that process, how that happens through time. And one that we're maybe familiar with from the program this summer is Schrodinger's equation. So this describes how qubits in a quantum computer act, but also just even the electrons in a hydrogen atom, the nucleons in a nucleus, basically any of these low-level quantum systems that are described by Schrodinger's equation, which is also a partial differential equation. But ultimately, if we want to solve these things, we need a numerical method that we run on a computer. So the governing equation in this case for atmospheric radiation transfer is something called the radiation transfer equation, or the Boltzmann transport equation. And this basically describes the physics of how incoming solar radiation in the form of electromagnetic radiation and photons interacts with both the atmosphere and the surface. So this is radiation transport. How is radiation transported through the atmosphere, down and up as it moves through? So now to give you a sense of why I picked this problem, the computational implementation of this this equation of radiation transport was initially worked out for astrophysics and nuclear energy applications way back in the 1930s and 40s. While it got a lot of its, I guess, theoretical development in the nuclear energy community here, it shows up in a lot of different things. So like the solar radiance problem, that's one application of radiation transport. Heat transfer, like in an oven. So this glowing heat element here is actually radiating infrared energy down onto your food when you're cooking it. So modeling that heat transfer process is important for a lot of industrial systems. Astrophysics, so in this case, it's a supernova. So when the star explodes, basically it's a radiative process as the energy is being transferred throughout the star. Graphics rendering. So if you're actually, when you want to render a scene like this one here, what you're basically doing is modeling how light moves through the particular scene that you're trying to display. So that is an instance of the radiation transport equation. You're modeling how light is moving through your scene in order to render it properly on the screen. Like I mentioned, nuclear energy, you want to know how neutrons and gammas are moving through the reactor to get a sense of where the power is going. Also in medicine, many times if you're having a medical procedure done related to like cancer treatment or imaging, there's almost always one of the doctors is running a calculation to make sure that you're not going to get overexposed to radiation. That's a radiation transfer application as well. And finally, rarefied gases. So if you have a gas like the upper atmosphere, where let's say it's the molecules and atoms are too far apart to interact with each other, they still interact with things that are moving through the medium. And so the Boltzmann transport equation describes these rarefied gases. And in this case, a spacecraft re-entering is interacting with those molecules. And so the transport equation will describe how they interact with that surface as it's moving through it. And I promise this is like one of the only equations I'm going to show today. But the Boltzmann transport equation is basically a balance equation. So you're basically accounting for sources and sinks, and ultimately how that's changing through time. So it's a 7-dimensional state space. You're modeling. You have some function f that describes where are the particles in space. So that's x, y, and z. Where are they traveling in their direction? So you have 2 angle variables to describe that. What is their energy or their velocity? And where in time are we? So 7 dimensions. So you have the change in time is going to be what are your sources? And then you take your source and then you subtract from that, okay, how many stream away? So that how many have moved out of the space that you're in? And then how many have collided? So the collision basically takes it out of that energy and velocity space and puts it in another one. So remember, we're looking at it in this sort of this discretized differential space here. And this is just a balance equation. And it works for any kind of particle. So any rarefied gas, neutrons, photons, electrons. But it's valid under the assumption that all the particles are the same type here, and the particles do not interact with each other. Once they're all close together and they're interacting with each other, then this equation needs additional nonlinear terms that ultimately will turn it into something looking like the Navier-Stokes equations. So this is a linearized version of that. And so get you a sense of like, what does that look like in a state space here? So you have some time t, right? So you have streaming terms. So you have photons or particles entering and leaving. You have sources. So maybe some photon was born here in this this green area and moved into your state space. And some others were lost through collisions. And then what does it look like in the next time step? So maybe you have a new source is born here, you have another one that leaks out, and so on. So basically, you're basically tracking the balance of particles in a system through time. And then depending on what the specific physics you are, whether you're talking about the atmosphere or whether you're talking about a nuclear system, the terms of this equation can vary considerably, but the basic idea is that it's a balance equation. Okay. So that's the continuous description of the problem. How do we actually map that to a computer? So when we have a PDE, a partial differential equation, those are usually defined continuously in time and space, usually. Now, to run it on a computer, you need a discrete representation. You can think of that, okay, well, you have integers, you have bits that are ones and zeros, you have a finite number of them, so you have to come up with a finite description of the problem. So that is called discretization, the process of turning an infinitely continuous PDE into a finite set of pieces that you can compute numerically. To do that, that's where you go talk to an applied mathematician who knows numerical analysis, who basically will take this this PDE and come up with a discrete representation of it that kind of operates on a grid in effect, and you prove that as you make the individual discretized pieces of that problem smaller and smaller, that the solution will stably converge to the true unique solution to that problem. right? So if you look at you sort of as an image depiction of that, if you look at this rabbit here, it's triangulated on a surface with triangles, polygons. As I make the triangle smaller and smaller, it converges on what that rabbit actually would look like in real life. So it's the same idea with a PDE solution. As you make the grid smaller and smaller, it converges to the true solution if you formulated the discretization properly. Same thing with the stability. So in other words, as I change the the difference between the discrete version and the exact version, there should still be some stable error involved between the discrete version and the continuous version. And then once you have the discretized version, you basically represent each grid point as an equation in a large system of linear equations. And then you use linear algebra to then find the solution of the problem. So there's lots of different discretizations out there for PDEs, but they all basically work on the same general idea where you take your geometry, your space, and you divide it up into a mesh of cells. So this can be like a Cartesian grid. It can be a deformed Cartesian grid, like in the picture here. So this is an airplane wing. And then instead of having just a regular grid, they took a grid and folded it all the way around the wing to give it a slightly more compact representation. So that's called a structured grid because it has that logical connectivity structure to it. Because in topological space, I guess it's still Cartesian. But if you can also have what's called an unstructured mesh. So this is where you have triangles, tetrahedra, polyhedra, and you just fill space with these unstructured elements. And then you have, in addition to the values on each mesh point, you also are storing the graph of connectivity between each mesh point in order to traverse it when you're doing the solution. So these are better at modeling complex geometries because you're not constrained to a particular element shape or type. And so you'll run into both when you're solving these kinds of equations. Okay, so then once you've got this mesh defined, now you need to define what is the discretization format I'm going to use. So there's three big categories of discretizations, and then within each category, there's probably dozens of flavors of it. But the first is finite difference. So this is basically where you take a derivative and instead of defining it as a infinitesimally small derivative, it's a finite difference. So you're just basically subtracting the difference between 2 points and taking an average. It's a little more complicated than that. You actually do a Taylor expansion and you derive a finite difference, what's called a finite difference stencil. So this is a 5-point stencil here in this grid. But basically you're using differences to describe the derivative part of the equation. So that's probably the simplest way of doing it. And that's generally limited to structured grids. There are unstructured versions of finite difference, but generally it's a structured grid discretization. The next one is finite volume. So in this one, you're actually computing the balance of material flows through many individual cells. So it's basically an accounting process. So your outflow from one cell equals the inflow to the next cell and so on. And you're basically enforcing conservation laws between each of your cells. That shows up a lot in like fluid flow type problems. Those are very often finite volume solutions. And then finally, there's the finite element method. This one's mathematically a little bit more sophisticated, but the long and short of it is you're basically taking, instead of the original equation, you're converting it to something called the weak form. So the weak form is you're basically invoking something called Green's theorem to basically describe the solution around the outer boundary of an element of space can be put in terms of what the solution inside that element of space is. And so the way the finite element method works is that you create that weak form of the PDE, and then you're solving a minimization problem of some basis functions that are expanded on each element. And so that's a very terse description of what finite elements are. There's dozens of flavors of it, but that's the general idea: is you're taking the weak form and you're trying to find a variational solution to the problem. Now that you've got a discretized solution, now you have to run what's called the solver. So this is actually a linear algebra solver, where you're either solving AX equals B by taking the inverse of the matrix A, or a similar, if you're doing an eigenvalue problem like Schrödinger's equation, there's going to be a similar description of this. But in any case, each grid point can be represented as an equation in a system of equations and unknowns. And then you represent those with a matrix. And then in order to get then you have some answer to the equation B, that's your source term. And in order to get the solution X, which is in the case of radiation transport is going to be the intensity of radiation at a particular point in space. You invert the matrix and apply that to the source term. So inverting the matrix gives us the solution vector. Now that inversion is the whole crux of the problem, right? So that can either be a direct process. So if you do a direct solve, this is something like Gaussian elimination, if you're familiar. Or you can use iterative methods. So an iterative solve, where you have some initial guess, you apply the inverse operator to it, and you get an answer, and you iterate again, you get a new answer, and you keep iterating until the solution converges to within some tolerance. Iterative methods tend to be used on very large problems where it's too difficult to store the entire matrix in memory. Direct solves tend to be more smaller problems, but there's not necessarily a strict limitation on either one. So making it concrete again, what are the numerical methods for radiative transfers? Because this is tends to be a much more complicated equation. Like most PDEs, there's no general closed form solution except in some very rare like 1D cases. So we basically, once again, need to convert that into a discrete representation and run it on a computer. And there's three big ways that this is solved right now. The first one is the Monte Carlo method, which I'll get into in a second. There's another one called spherical harmonics, and there's another one called discrete ordinates. So I'll go through all three very quickly here. Monte Carlo is probably the highest fidelity version of this solution method you can do, because fundamentally radiation transport is a discrete process. When you think about it, photons are discrete packets of light, of energy. And so individual light particles interact with the surrounding environment in discrete events. So you have individual photons doing discrete things like scattering off an atom or being absorbed by an atom. They're all discrete events that are occurring, and they're all happening probabilistically. So every time a photon interacts with an atom in the medium, it has a certain chance of doing one particular interaction, a certain chance of doing another particular interaction. It's quantum mechanical, so it's going to be probabilistic. So in this case, instead of discretizing the equation, we actually just directly simulate and tally these discrete individual particle motions and interactions. And so we treat it like a statistical sampling process, like a real experiment. So we have the sun up here that's emitting photons at some angle, at some initial angle and some initial wavelength, and they come through the atmosphere. And then every time you encounter an atom, you roll the dice to figure out what's going to happen. Is it going to be absorbed? Is it going to scatter? What direction is it going to scatter? And so on. And you track it all the way through until it finally is absorbed. And then you tally that energy deposition. So that's analogous to a real experiment or observation. And so you run many, many trials of this and build up a statistical picture of what the full solution looks like. So this is the gold standard for accuracy. This can handle arbitrarily complex physical processes and geometries. You're really only limited by the data that you have to put into it. You can, the simplest Monte Carlo you can write is just a coin flip, right? You just have a random number generator and say, okay, if it's this big, I get a 1, this big, I get a 0, and then tally it up. You should get 50-50. Same thing you could do with a pair of dice, a deck of cards. This picture here is actually a particle accelerator. I think this is from the LHC. So you can actually, you have these heavy hadrons coming in here, and then they're creating these showers of muons, electrons, neutrons, and then you're tracking them through space to figure out where are they hitting detectors. So it shows up in particle physics too. It winds up looking something like this. So as you can see, as you run many, many particle histories, you're building up this sort of statistical picture of where everything is going. And because it's a Poisson process, right? The solution converges as 1 over the square root of n, where n is the number of trials that you're running. So if you want 1% error, you got to run 10,000 problems or 10,000 histories roughly. And so you can do some statistical tricks to reduce the variance on that. So you don't need to run nearly as many histories, but it does converge very slowly. So that's sort of the trade-off that you get for the high accuracy. Interestingly, now when you think of this from like quantum computing perspective, you can provide at least a quadratic improvement in this convergence rate. just by formulating it as kind of a Grover search problem. But that sort of neglects the fact that there's going to be some constant overhead involved with that. So there's going to be data movement. You're going to have to do data lookups. So theoretically, there's a quadratic improvement. Whether or not that's enough to overcome the constant overhead is an open question. So when Monte Carlo is infeasible, though, we can that's when we can instead use a discretization method on the equation itself. So this is what's called the deterministic method. A discrete form of the Boltzmann transport equation is a deterministic form of that. So you can discretize space with finite difference, finite volume, finite element methods. But that's just space, right? We still have these other dimensions in angle and energy and time. So we have to discretize those too. So how do we handle the other dimensions? The first thing you could do is ignore them. You can assume everything is one energy or one wavelength. So that's a monoenergetic approximation. You can assume that it's a diffusion problem rather than a transport problem, in which case all your interactions occur isotropically. And to give you sort of an intuition of what this would look like, I actually did this experiment in my kitchen here. You shine a laser through a glass of water. Initially, clear water. That's a transport problem. So you can see the light is being transported from one side of the glass to the other, and it undergoes a reflection on the other side. So now let's add some scattering to this problem, right? So there's right now, the light is just streaming through. There's no scattering collisions between, there's very little scattering collisions between the photons of light in the water. So I put a drop of milk in it, right? So now you can see, well, the laser beam is spreading out a little bit and the water is very cloudy. So if you look closely at this picture here, you can see it's not a straight beam anymore. It's kind of this divergent fan. Put another drop of milk in, you can see that fan gets even wider. And you add even more, now it's starting to look more like a spherical distribution. So rather than being a point beam source of light, now I have a spherical source of light. So that's a diffusion problem. So now you can approximate the transport problem as a diffusion problem. You just save yourself a lot of computation having to deal with the angular variable. You can also do a steady state approximation. So you can assume that the radiation input is constant with time. You don't have to handle the time variable. You don't have to do time stepping. So sometimes those are valid approximations to make. And if you can make them, it's generally recommended that you do because it saves a lot of time. But if you can't, what you can do is when you go and discretize these other variables, in terms of wavelength and energy, what you can do is you can break up the spectrum into discrete bins or groups. So this is what the incident spectrum of light looks like on the Earth. So you can see the yellow curve is sort of an ideal black body spectrum. The orange is what actually is hitting the top of the atmosphere. And then when you look at what's actually hitting the Earth's surface, it looks kind of more like the lower curve here, where you have the visible region and the black region, where you have these different windows where the sunlight is being absorbed almost completely. So you can break that up into individual bins rather than a continuous distribution. And so that could save you some time depending on how you discretize that. Similarly, with time, you have to break time up into discrete steps. So you have some differencing in time. If you're doing just ordinary differential equations and you had no spatial component, typically what you are tracking then is that discrete time stepping. So how does something change with time? And then sort of the one that defines most of these methods is how do you discretize the angle and direction of motion? So you can do things like you approximate the angular variable using a set of special functions called the spherical harmonics. You can just choose discrete angles to solve the problem at, so that's called discrete ordinates. Or you can do things more sophisticated, like expanding it in wavelets, like sort of like the signal processing method. And so there's a whole zoo of these angular discretization methods. The two most common, though, are the spherical harmonics and discrete ordinates method. So in the spherical harmonics method, what you're basically doing is you're treating this angular variable, this angular intensity of the radiation, as a linear combination of these basis functions. And if you look at this picture here, you may recognize these as the same spherical harmonics from quantum mechanics, because they are the same. And basically what you're doing is you're adjusting the coefficients on each of these little basis functions here to see which is contributing most to the angular component of the flux, of the energy. And as you add more of these basis functions, you get a more accurate convergent answer, but obviously you have the trade-off with a more expensive computation. And as you get to higher order terms and higher dimensions, it becomes algorithmically challenging because the coupling between all these different functions and spaces becomes very complex. It's not necessarily a one-to-one decomposition. So it becomes harder to solve as you get bigger in order and in dimension. But like I said, it's the same functions that show up in quantum mechanics. So the picture here, is maybe familiar to a lot of people. And this picture at the bottom here is using the spherical harmonics to solve a radiative heat transfer problem. So in this case, a commercial solver, COMSOL, was used for this picture. So discrete ordinates. This tends to be one of the more common deterministic modeling methods. In this one, you're basically choosing a few discrete angles to solve along. So you basically have this sphere, this unit sphere, and then you define some points that you want to solve on, and you give them a weight, and then you solve the equations along each of those directions. And then you use a numerical quadrature, an integration rule, to sum them all up with some weighted sum. And then that'll give you the full angular picture of the problem. So as you run more angles, you get more accuracy, but once again, you get more computation. So it'll be, basically each angle vector is a unit vector pointing to some position on the unit sphere here. And if you're looking at sort of the atmospheric transfer problem here, right? It's the same idea. You have light coming in at some angle, and then as it scatters, it changes direction, right? So you basically want to solve the problem for each angular direction. Same thing here as you're getting closer to the surface. So you can see here what they did is they actually increased the resolution of their grid closer to the surface, because naturally, just because there's more interactions happening near the surface here. Okay, timeout. That was a lot of stuff. So are there any questions in the meantime? We'll catch up on that.
Okay. Yes, so thanks a lot, Brian. And there are a lot of questions on this talk. Let me just quickly start with a few. So one question was on why are we preferring PDEs instead of ordinary differential equations?
Right. So you can think of a PDE has a multi-dimensional spatial component to it. And the ODE is kind of like a one variable, right? So think of like, population growth of like bacteria in a petri dish, or maybe like radioactive decay, right? You're tracking one independent variable against one dependent variable. So that would be an ODE, right? You basically have a one-to-one. A PDE is when now you have multiple additional variables that you have to track. So typically when you have, these real world systems like that, it's a 3D world by definition. So it's going to be a PDE. Now, if you can collapse some of those dimensions down and treat it as a zero-dimensional problem, then you have an ODE. So depending on what you're doing, you can approximate some of these things as an ODE if you don't necessarily care about the spatial distribution of things.
Right. Another question is from Mohammad Reza from Iran, and he asked that discretization is at the heart of computing. But are there any cases where reshaping of some continuous mathematics is not exactly appropriate? And maybe we can use some continuous distribution for computational methods.
Right. So it gets tricky, right? Because computers by definition are discrete, right? You can't, even if you're representing real numbers with, say, floating point numbers, those are ultimately going to be discrete representations just by the finite precision you get. So the ways you can get around this, like let's say you really do need as continuous a description as possible. That's where things like Monte Carlo come in, because so you don't have to use you have to use the discrete representation. You can make the mesh, the grid that you're solving on finer. That's sort of the most straightforward but most expensive way of dealing with the need for as close to continuity as you can get. Or you can sort of raise the order of the basis functions that you're using to solve, right? So let's say if you're doing finite difference, for example, instead of using a 5-point stencil, you can do a 9-point stencil. So include those next nearest neighbors as well. If you're using finite elements, on each element you have some basis function, right? So that's typically like a linear function. You can use a quadratic function. You can use a cubic function, all the way up to as high order as you want. So that's other ways of getting closer to the continuous representation. So none of that comes for free, right? So if you really want an actual continuous computation of something, that's where you have to go to like an analog computer, or even a quantum computer can do things continuously when you're in the coherent space. You still get a discrete answer out, but if you can do the computation in the coherent space and still extract the information you want, then that's a way of preserving that continuity.
Earlier, you also had a slide representing finite difference, finite element, and finite volume methods. Could you briefly share what is the difference between these three methods and what are the specific applications suited to each of these methods with respect to climate and AI model?
Right. Okay. So the differences of each one of these I kind of covered here, but once again, just to simplify it, a finite difference, you're representing the derivative term as a literal difference, because as you make differences smaller and smaller, just that fundamental theory of calculus, right? You basically you recover a derivative as this h becomes infinitely small. Finite volume is, once again, you're basically doing a mass and momentum and energy balance from discrete regions of space. So if you have an equation that describes how material flows from one region of space to another, and you have discrete volumes representing that, you do an accounting of where the mass and momentum are going as they move through cells, and then once again you can use that to solve the problem. With finite elements, what you're doing is you're converting the original PDE into the weak form, and then you're treating the solution as an expansion of basis functions. And then you're minimizing the coefficients of those functions such that it matches the solution of the problem. So now where does this come up in atmospheric modeling, climate modeling, and things like that? They all show up. So typically finite difference, you're using a structured grid. It's hard to define this on something that's not Cartesian like this. It's not impossible. People definitely do it. But it tends to be better suited for these these Cartesian type problems. Now, if you look at this picture here of how they drew the grid on the Earth, that's definitely not a Cartesian mesh, right? That's a completely unstructured polyhedral mesh. So in a situation like that, typically what you're doing is either finite volume or finite element. With finite element, it's typically formulated on things like triangles and squares and sort of the three-dimensional components of those. But what you can do with a strange-looking polygon like this is you can break it down into individual triangles as you're solving it. There are other formulations that let you solve on polyhedra. Something like this is probably going to be more of finite volume, but finite element could be used on an unstructured grid like this as well, on a hexagonal grid like this.
Ira from Indonesia asked that you mentioned time, angle, energy, fluid dynamics, and yeah, like there must be a lot of complex variables involved when we are trying to model climate. On a pragmatic approach, how many dimensions do you think we could map on a quantum computer with the current development?
Right. So where quantum computers are today is very limited, right? And as you probably have probably experienced when actually implementing things on a quantum computer, it's very challenging. So right now, the best quantum computers can do like a small one-dimensional problem for PDEs. And what I'll get to it in a second is it's actually an open question which PDEs are going to be advantageous on a quantum computer or not, just because the structures of them could be radically different depending on what it is you're trying to solve. Now, one thing that does show up a lot, especially in a very complex multiphysics problem like climate modeling, is that you're generally not rolling this all into one big equation. You can, but typically and just pragmatically, the way these things are solved is each individual equation is broken up into its own computer program almost. So you'll run, and then there's this big outer loop that's kind of orchestrating the whole thing. So you basically solve the radiation part, right? Okay, where did the energy go? Then using where that energy went, you solve, say, the fluid dynamics part. And okay, you solved the fluid dynamics part, and now maybe there was some evaporation or condensation that took place. You have some other constitutive relationship that describes, based off the energy that contained in that system, how much water is evaporating, how much water is condensing. And then you have to couple that to, okay, what clouds formed? How did the cloud form based off of the local temperature, pressure, humidity, all those variables. So you can see it gets very complicated, but each one of those little things is its own subroutine or computer program that then gets coupled together in this large framework that's running on a supercomputer.
Right. One last question before we can move forward with your session, Ryan, is Varta from India asked that how do you balance between accuracy and computational cost when you're trying to model such a huge problem on both AI as well as quantum techniques?
Right. So it depends on what you're trying to do. For example, if you're, let's say you're doing a weather forecast, right? And you want to know within a particular region of the world, when is it going to rain? How much is it going to rain? If I, the user of a weather app, would like that to be as accurate as possible, you're going to be using a lot more computation to make that, to reduce the uncertainty on that weather forecast. Now, let's say I just want to know, is it going to rain at all today? I don't need to do as nearly heavy, high resolution computation to do that. I just need to know generally what's the weather doing in this area. So that's kind of you can back off on the resolution in order to get something like that. Same thing shows up in engineering, right? If you really want to know to within 1%, how is this component going to perform? You have to do a very high resolution calculation to do that. If I just need to, let's say I need to run 1 million cases of this component under different loading conditions and things like that, I don't have the time or the ability to run very high resolution calculations. I have to reduce the order of that model to something that can run very, very quickly. So that's when you would back off on the resolution and instead go for speed.
Okay, thanks a lot, Brian. And now back over to you.
All right. So now on to the second part of this, how we're doing on time here. Okay. So now for the fun part, actually solving the problem. So we've done all this modeling, we've done all this discretization. Now we actually need to turn that into a computer program. So what does that actually look like in practice? So when you have a big scientific code like this, whether it's an engineering code, whether it's a climate modeling code, whether whatever, typically you're using a compiled language to do this. So this is going to be C++, Fortran are two of the most common ones for this. Julia is a newer language that's starting to show up a lot more, but they all typically compile down to machine code that can be highly optimized for a particular hardware. So when you run on a very large computer, most of these problems are too big to fit in memory. So you'll wind up with, you try to have the entire Earth, you have lots of grid points. That's not necessarily going to fit in typically 128, 256 gigabytes of memory on a particular node. So now you have to distribute that over many, many nodes of computers. So the way that's typically done is with something called message passing interface. So it's MPI. So it's basically you have several instances of the program kernel running on different CPUs of the machine, and each gets its own little slice of memory. And then you have explicit communication between the different processors that share data, share solution data. So if you're trying to compute something on this mesh, right, but the mesh is broken down by domain across many processors, once your solution gets to the edge of the mesh, you have to communicate that to the other processor that has the other piece of your problem, so that way it can continue the computation. So it's this very highly orchestrated calculation that you have to do. Now, if you're on a node, if you have multiple CPUs, but let's say it's just one computer, you can do what's called shared memory processing using a system called OpenMP, or just general multi-threading. This is a multi-threading process. So this is basically taking one slice of memory that every processor on that computer has access to, and it's each thread is working on a different part of it at the same time, you hope. This is actually a challenging thing to implement because you don't want different threads stepping on each other, overwriting data, corrupting data. So you have to, when you write multi-threaded applications, you have to be careful that each thread knows which data it's accessing and the other threads are locked from interacting with it. So that way you're not inadvertently corrupting your data. You can also run things on GPUs. So this is obviously a lot of the machine learning applications wind up on GPUs. So do numerical computing applications related to PDE solving. GPUs are very good at certain kinds of matrix calculations, Although when it comes to things like transport, like we've been talking about, typically there are spatial dependencies. So basically you have to solve one grid cell before you can solve the next grid cells. That's a little harder to deal with on a GPU than it is saying just solving a whole, inverting a whole matrix like that. So depending on the structure of the problem, GPUs can give you speed up somewhere in the range of factor of 5 to a factor of 100, depending on what it is. But it really is dependent on the structure of the matrix that you're trying to invert. And then when you have all this data being generated by this giant computation, so you also need a way of storing it. So typically in these HPC applications, HDF5 is a common file format. Specifically for climate and atmospheric calculations, the NetCDF format is a subset of HDF5 that is used for storing this data. And so if you look at the picture on the upper right here, you typically have this big, multi-dimensional grid of temperature. So you have XYZ temperature, XYZ pressure, elevation, land cover, latitude, longitude, time step. All this stuff gets put into these hyper slabs, they call them, and then saved to an HDF5 file. Now for the actual linear algebra solver, it's very rare that you, on a large scale application, that you would implement that part by yourself. There are very well-known, well-tested, well-worn libraries for doing this. PETSI, Trilinos are two ones for very large linear algebra calculations. BLAS, LAPACK are also sort of the very common specifications for linear algebra, primarily that run on a single node. But you would typically use a library like this. You wouldn't necessarily go to writing that yourself. Once you start moving to heterogeneous architectures like GPUs, many core, SIMD, APUs, you can write the CUDA code yourself, but you don't necessarily know what vendor's hardware you're going to get. So especially on the larger HPC systems, they're not always buying NVIDIA cards. Sometimes they're buying AMD cards. Sometimes they're buying Intel cards. So what they've developed are these performance portability libraries. So Cocos is one, Raja is another one. These basically abstract away all the underlying GPU hardware, and you're just writing regular old C++, and then it tells the compiler how to map that to the particular hardware you're targeting. And then when it comes to actually writing the discretizations, it can go a number of ways with this, right? You can write the discretization yourself, or there are some frameworks out there that let you write these discretizations for you. So MFEM is one for finite element methods. There's others like Deal2, Phoenix, all sort of generic finite element libraries where you can write your. It has sort of the basics of finite element discretization written into it. You just have to customize it a little bit. OpenFOAM is for finite volume for fluid solver, so you can write your own fluid solving routines using OpenFOAM. AMREX is an adaptive mesh refinement library, primarily for things, finite difference is one. You can write finite elements on it as well, and as well as finite volume, but it will support all those different discretizations on structured grids. And then finally, you have to have something that controls interfaces and post-processes all this stuff. And so Python is very common for all of this, for orchestrating all this. Typically, what you'll find is the core solver is written in something like C++ or Fortran, and then you've written a Python wrapper that makes it a lot easier for your users to use. So people are typically, using Python for a lot of things. So you're basically interacting with Python, but under the hood, after you've hit enter and started off the calculation, it's running on C++ or Fortran under the hood. Or good old Bash, right? You can use that to sort of script everything and orchestrate it all. So writing a PDE solver is usually the easy part. And I say easy in that it's something that a lot of people do it as part of coursework in school. Writing something like a finite difference that solves the heat equation, that you could probably do that in an afternoon if you're good at programming. But when you have to do this in a professional quality type software system that people have to interact with and run many different types of generalized cases on, these other things get very hard and require a lot of work to implement properly. So you have to basically have ways that handle the boundary conditions, create the geometry. So you basically need to interact with a CAD system or have your own CAD system that creates the geometry. You have to generate the mesh, which that was my first job out of school, and that's that's a very, very difficult problem to do in a general way. So there's also mesh generators out there that you can get and interface with. And you have to write the user interface itself. So for visualization, typically tools like ParaView, VTK, for creating the 3D graphics to actually display your solution. So these are all things that you have to take into account when you're actually writing a software tool that lots of people are going to use beyond just yourself or a small group of people. And if you actually want this code to be used and maintained by other people after maybe you've moved on to something else, it has to be done right. So this is where all these sort of the good software development practices come in. You don't want something that looks like this power plug here. You don't want something that looks like a Rube Goldberg machine of using a self-operating napkin. You want something that is transparent to the people who maintain it and transparent to the people who use it. So a lot of people, especially in scientific fields that are not necessarily steeped in computer science, it's kind of glossed over in sort of the programming training of what does it actually mean to write good scientific software. So the advice I usually give to people is this: learn version control. With typically Git, doesn't have to be, but Git is the most common one. If you can track your changes and you can roll back your changes and you just keep track of everything as you're going, that solves so many problems. So learn Git. And it helps if you learn Git with multiple people, because once you're operating on a team, it's very difficult to operate in any other way other than with a version control system like this. So learning Git by yourself is one thing that's highly recommended. Learning Git when you have a team is also a very good skill to have if software development is something that you're interested in going into. The second thing, documentation. Tools like Sphinx, Doxygen, these are all sort of automated systems that will parse your code and generate, if nothing else, just lists of what variables are. That's also very helpful for people that are trying to maintain your code. But go the step further and actually write descriptions of what each function, each class, what everything does. So that way, a user is confused at what something is doing, or somebody coming after you is trying to maintain this. It goes a long way at just maintaining quality. And the big one, especially for scientific codes, is this testing and quality assurance. Unit testing is one that's common to pretty much all software development applications. So for example, in Python, you typically use something like PyTest. So you write small little test functions that will test another function in your code to make sure that given a certain input, it gives you the expected output. Same thing, C++, there's a framework that I really like that's called DocTest. It's very lightweight, but it behaves very, very similarly to PyTest. And then in scientific code, you have to go a step further. Verification and validation. So verification is basically you're showing that you're solving the equations correctly. So if I've discretized the equation and I give it this set of input parameters, I verify that it is solving that equation correctly. Validation is showing that your code is solving the correct equations. In other words, that you're matching nature. So you typically, in this case, you'll have a benchmark problem that somebody did in the laboratory, but described really well. You'll define that problem, put it in your code, run it, and verify that your answer matches the experiment to within some acceptable level of error. If you can do these things, you'll be way ahead of all your peers in scientific computing. Just understanding these three core pieces of software quality assurance puts you light years ahead of everybody else going into this field. So I highly recommend learning about them more. So like I was saying, verification is testing to make sure the code is solving the equations correctly. So typically the way you do this is one of two ways. Typically you have an analytical solution. So like I said before, PDEs don't usually have analytical solutions, but they do for some certain subset of cases. So define those analytical solutions and in your problem, run them and then compare your numerical answer with the analytical answer, and it should match to within some tolerance. So that's one way of verifying. The other way of verifying is with something called a manufactured solution. So in this case, instead of solving for x, instead of solving ax equals b, what you're doing is you're defining x and you're solving for b. So you're just running the operator through. So in that case, you've manufactured the solution, and then here you're just verifying that the operator is correct and operating correctly. Now, validation is once again making sure that you're matching reality. So in this case, like I said, you got to do a benchmark experiment. So this picture right here is a very common fluid dynamics benchmark called the lid-driven cavity. So what it is a box of water, and on top is a conveyor belt. And the conveyor belt is running, and it's creating this vortex. So as the vortex is running, this is a very common benchmark application for fluid dynamics codes. So what you would do in the experiment is you would typically have a laser and some sort of particles in the fluid to measure this vortex and the velocity profile of each of the particles, and you would match it against the experiment like this to verify that your code is within some tolerance. Similarly, if you, let's say now you're doing the Earth, right? But we don't have an extra Earth to run experiments on. So in this case, what we could do is take observations. We know what the weather was like in the past, we know what the climate was like in the past. We can take our model and use some initial conditions. So what was the Earth like on January 1st and run it forward to today, July 1st, and say, okay, well, how well did the weather patterns over the past 6 months in this model match the real weather patterns that we had over the past 6 months in real life? And then finally, you can do what's called Bayesian calibration. So this way, you're basically taking the data points that you know from the real world, and you're running them in your model, and you get some error on it, and then you can also sort of estimate the error in sort of the interpolated spaces as well. Okay, so now on to the main part of sort of how does AI and quantum help all this? How does it primarily accelerate these large scientific computations? So first off, AI in this context almost always means machine learning. And as we've heard in some of the past talks, there's two kinds of machine learning. There's predictive and generative. Predictive is basically you're approximating f of x. So I have some input. In this case, it's a dog. So x equals this dog, and f of x is returning is this a dog or a cat. So x is the image, and then y is answer dog or cat. So I put it through this neural network, and then I get an answer. So it's predicting what is this given the input. Generative is you're basically creating an approximation of the probability distribution that generates the data. So in this case, in this bottom picture here, this is a generative model called a normalizing flow, real NVP. And what you're basically doing is you're sampling from some distribution Z, you're feeding it back through this model, and it should generate a picture of a dog if it was trained on dogs. So typically, if you were to think back a couple of years to, there was a popular website called This Person Does Not Exist. That is using a generative model like this. It has some underlying probability distribution that represents what faces look like. And as you sample from that distribution, it's sort of interpolating on that distribution to generate a new face. ChatGPT is doing the exact same thing, just on a much, much larger scale. You have it's trained on this immense data set of written language. And then you give it some input prompt, and based off that prompt, it samples from this probability distribution of how the rest of that conversation ought to go, based off of the structures in the written language that's been on the internet that it was trained on. So that's all it's doing. It's just sampling from a distribution. There are other types of AI out there besides machine learning. And they typically get less attention these days because machine learning has been extremely effective at doing lots of things. But there's also formal methods. So these are more like the logic and reasoning type methods of AI. This is for more like decision-making problems, search and planning. So now that you've actually, you have some idea of, what the solution is, what do I do in order to get to the solution I want? So this is more active participation in the solution process. And there's also neurosymbolic. So sort of combining the machine learning with the formal methods to get something that can not only recognize patterns, but also accurately reason and act on them. And then in general, in scientific computing, Bayesian methods specifically, so methods that incorporate some level of probability and uncertainty into them, nearly always give richer information. So this picture on the top here with sort of the image recognizer, these will typically give you like it'll give you a dog, it'll give you a cat, but it'll say, they don't usually tell you how certain or uncertain they are. So methods that give you a measure of uncertainty are typically far more useful in scientific computing than ones that don't, because you want to know how close to the real answer you might or might not be, because that can inform decision-making down the road. So once you have machine learning, then what does that typically entail when you're talking about accelerating scientific computing? That typically boils down to what's called statistical emulation. So you train a machine learning model, which is something in this context, sometimes called a surrogate model or a meta model. on the behavior of the simulation. So you can run lots of simulations. So this picture here shows a Latin hypercube sampling. So this is basically of all the parameters that you have that go into your simulation, you create some subset of them because you don't want to run everything. It's just going to take forever. So you pick what parts of this parameter space do I want to run. You generate the training data, which in this case is you run those simulations and you get the solution. You give those solutions to a model. So you train the model. And then you evaluate the results. So basically you cross-validate your emulated results with other simulations that you withheld from the training set. So very similar to any other standard machine learning problem, right? So in this case, you have this cycle, right? So if you need to choose some more simulations to run to improve your predictions, you just run that process again and again and again. And some of these, like I said before, will provide uncertainty estimates. So if let's say you sample a new parameter from in this space, you want to make sure that it's within some tolerance, right? And if it's not, then you'll maybe run a few more simulations to bring down the error. So you can also include data in this. So you have these computational simulations with measured data. So let's say I have some weather simulation or climate simulation. Well, I also have weather stations that are out there. I also have buoys out there that are measuring temperature, pressure, precipitation. I'm sending up weather balloons. I'm taking measurements with satellites. I've got radar images. You have all these other data that are being generated that you can incorporate with the simulation in sort of a Bayes theorem framework, and you can use those to sort of decrease the uncertainty and increase the predictive capability of the simulation. And similarly, you can also use this data to train a model, much like in the previous slide, to replace a simulation component. So in this case, we don't know what the governing equation is, but we have data on what the behavior is. So maybe we can use something like a trained model like that in order to create a simulation component based off of the observations. So statistical emulation, it's as opposed to a simulation where we're actually solving the governing equation. A statistical emulation is we're basically taking the statistics of the problem and creating a model that either predicts or generates new solutions based off what we know of the statistics of how those other simulations were run. So typically these are things like Gaussian processes. That's typically the gold standard. So Gaussian process is it's a kernel-based method. You run lots of training points here, and then you create a plot that sort of represents all the possible functions that could fit those points. As you can see in the plot here, the regions where no data was taken, the uncertainty is fairly high, but in the regions where data was taken, the uncertainty band is very low. So you can see this is a probabilistic method that gives you an uncertainty estimate. Problem with Gaussian processes is that they scale of O of n cubed, where n is your number of data points. So if you have a large data set, for example, say past 10,000 points, this isn't really going to be feasible for most large scale problems. So what you can do instead is use something called a Bayesian neural network. So a Bayesian neural network is something that approximates a Gaussian process. So there's a theorem out there that says in the limit of an infinitely wide neural network, you recover the behavior of a Gaussian process. So there's lots of different neural network methods out there that sort of approach this behavior. One that's pretty simple actually is to create an ensemble of neural networks and then create some anchoring points on the weights and biases on each node in the network. So that way you're effectively creating an approximation of a Gaussian process. There's more sophisticated methods out there, but that's a very simple one that could be implemented. Now, in terms of other generative models, things like normalizing flows, which are invertible neural networks. So this basically takes an input and creates an output. But what you can also do is you take an output and map back to the input that would have generated it. So it actually is a function that runs both ways. So it's particularly useful for when you have inverse problems. So let's say in the context of solar radiation, you want to measure how much infrared is getting out of the atmosphere. So maybe you'll have satellites in space that are taking infrared measurements. What you might do in that case is saying, okay, given that I'm recording this much energy on my satellite sensors, how much infrared energy is being trapped by the Earth? That's an inverse problem. So a model like this is useful for solving inverse problems. Same thing is another type of generative model, diffusion models. We're all familiar with Stable Diffusion. That can generate PDE solutions just as well as it can generate images, provided that there's some bounding on the simulation space for that. Generative adversarial networks, GANs, same idea. So you have a generator, it's generating things. You have a discriminator that's saying, is it correct, is it not? And then you're basically solving a saddle point problem to train these networks. And so we're all familiar with a lot of the frameworks that we used to do this. Scikit-learn, obviously the baseline machine learning library for very simple machine learning models. If we're talking Gaussian processes, GPyTorch, which sits on top of PyTorch, neural network library. That's typically one method of doing this. Scikit-learn has Gaussian processes as well. For this normalizing flow problem, you would use something like FlowTorch is one framework that does that. And for probabilistic methods in general, Pyro is a probabilistic programming language. Once again, that sits on top of PyTorch. That basically creates every variable in the problem as a statistical distribution rather than just a fixed point variable. So a case study from the literature. So this was actually a I have all the references for these at the end of the slides if people are interested. But this is basically a emulator of subgrid processes. So what's a subgrid process? So if you think back a couple slides where I showed that grid of the Earth, right? Well, obviously things are happening on smaller scales than each of those grid cells, right? You have clouds, you have, all the way down to individual raindrops, you have evaporation, condensation, things that they call microphysics, right? These are things that you cannot capture in the mesh that's on this grid. So we have to come up with, like we were talking about before, equations that represent these processes on the scale of a grid cell. But because these behaviors start to get chaotic and probabilistic, that's very difficult to do. So in this case, what the researchers did here is they created machine learning models of subgrid processes. So things that, given a temperature and pressure regime, concentrations of trace gases, and then presence of clouds and aerosols, you're basically creating a predictive model that says, what are the radiative properties of this? So in other words, as light's coming through it, what are the probabilities that it's going to be absorbed, reflected, and things like that? So basically, you're using all this information to create a parameterization. So the way they did that is they ran high resolution models that do resolve clouds. You can't simulate the whole Earth on that scale yet, but what they were doing is taking these mesoscale models that resolve clouds, that give more realistic results. So once again, if you look at this picture here, all these little things that you're seeing here zoomed in on a grid cell, that's what's happening at the subgrid scale. So that, you can't capture that necessarily in a simulation unless you resolve very fine length scales. So what they were doing is running simulations that solve these very fine length scales, training a model on that behavior, and then translating that to a whole Earth model that at each grid cell where you do know some parameters, you input those parameters, and the machine learning model gives you a prediction of what these subgrid processes would be capturing. So machine learning models trained on this super high resolution data and simulations are shown to improve the results of these global scale low resolution models. So in this particular paper, they actually did couple it to a model and show that they do show accurate formation of tropical weather, so tropical waves that turn into hurricanes, as well as accurate precipitation patterns as a function of latitude, given a time of the year. So this is sort of a showing of the concept of how you can use something like AI or machine learning to improve the accuracy of the model, or at least the resolved accuracy of the model using a machine learning based parameterization. So another way of handling machine learning in a scientific simulation context like this is something called physics-informed machine learning. We've heard about this a few times. And the reason you would do this is that just naive machine learning doesn't generalize well, right? You're just taking inputs and you're training them against outputs. That is complete black box information. There's no knowledge of physics in there. There's no knowledge of what is actually going on in the problem. It's just f of x and then x, and then you're trying to basically create a regression, a very high dimensional nonlinear regression of a function. That cannot extrapolate outside the training set, not reliably anyway. And you may wind up even with cases that violate physical laws like conservation of mass, energy, or momentum. So what you can do is you with physics-informed machine learning is it lets you include additional physics information that will at least create some guarantees of physical reality in your model. So you could basically include some of these PDE terms in the loss functions. So in this case, in the top picture here, it's kind of hard to see, but you can add some elements of the Navier-Stokes equations to a loss function so that your physics-informed neural network is preserving the conservation behavior of that governing equation. But in that case, you're still creating a model that is just emulating a solution, right? Sort of the newer and sort of interesting research area right now are these neural operators. So rather than trying to learn the solution, you're trying to learn the physics. You're trying to learn that matrix operator that represents your partial differential equation. And so there's a lot of different methods out there now that can accomplish this. Some work well, some don't, depending on particular problem. But this is a very promising method where you're actually generalizing to other geometries and other physical realizations of the problem rather than just a particular problem and particular solution. And you can also add constraints on output values. So in this case, you for example, wouldn't have a if you're simulating a cup of coffee here, you wouldn't have a negative temperature, right? It would be frozen. So you could add some constraints there, and then that gives you some bounds on your problem, but also some known bounds on validity when you're actually applying this to new problems. So this can be used sort of by itself as a generative model, or it can be used as a predictive model to extend the statistical emulation regime. Okay, so physics-informed machine learning is harder than it looks. You can wind up with instabilities in the solution depending on the architecture. Your hardware requirements, you typically need GPUs, right? You need to carefully assess your training time versus your solver time to see if it really is getting you any acceleration. So these are all things that need to go into the analysis of whether or not this is something you would choose to do. So there's physics-informed neural networks. In terms of operator-based solutions, you have Fourier operators. You have something called deep O-nets, deep operator nets. Mesh graph nets, where basically you have a graph neural network that is taking the form of your mesh on the problem. So lots of different methods out there. NVIDIA Modulus is a common open source framework for trying to implement some of this stuff. There's another one called DeepXDE that it's also open source, so you can implement a lot of these different types of models using these frameworks. Julia as well, in their scientific machine learning library, has a lot of physics-informed capability, particular for ODEs and ordinary differential equations. So here in this case study with this paper, this is aerosol microphysics. So things like dust and smoke and things. Once again, you're trying to figure out how does radiation incoming interact with this stuff and get reflected or absorbed. So there's a model out there called the M7 model that computes the the balance distribution and radiative properties of aerosol species. So given some aerosol concentration in the air, how does it interact with radiation? It's too expensive to run below a mesh size of 150 kilometers resolution. So if you mesh the Earth, if your mesh size is smaller than that, it gets too expensive to run on every single cell in that problem. So in this case, they created a physics-informed neural network model of that. So they put in some physics-based constraints in the training function, as well as hard constraints on the conservation of mass balance in the neural network architecture. And so this gives on a CPU, almost a 3x speed up over using the actual M7 model. But if it was transferred to a GPU, even when you take into account the data movement, it gives a 64x speed up of running that model, which is a significant increase. So if you're trying to run this in the context of a very large simulation, that gives a very good speed up. But that was a 15% error. So depending on your error tolerance, that may be good, that may not be good, but not saying anything about that here. That's just what they got. All right, now on to quantum. So in the case of PDEs, it's still an open research problem, whether or not quantum provides an advantage as a general case. There's some PDEs, obviously, we know that there is an advantage, Schrödinger equation being a particular instance of that. Particularly when you have dense couplings or something where if let's say you have an Ising model like this, if I flip one spin site, it affects the state of all the other spins in here. That's a strong correlation. So strongly correlated problems quantum computing will likely have an advantage for that type of thing. For other problems where there's not necessarily strong correlations, like the Laplace equation, probably not going to be much advantage on a quantum computer in that. You stick to classical solution methods there. So it's a lot of research and exploration is still going on to this space to figure out where the real advantages are. But we do know that the stronger correlations you have, particularly over longer distances, probably are going to work better on a quantum computer and have more advantage on a quantum computer than ones that don't. So in particular case of the radiation transfer problem, like I said before, Monte Carlo is one way of doing that. Monte Carlo is a random walk algorithm, and a random walk is possible when you have quantum states. So one way to think about it is if I have a marble going down this board of pegs here, it can bounce to the left, it can bounce to the right, let's say 50% probability, right? Well, Hadamard gate is the same thing. It's a 50-50 split in terms of whether a qubit is 1 or 0. So now if I put Hadamard gates everywhere instead of discrete choices, it turns out that the solution propagates faster through that type of system and accumulates faster through that type of system than it would classically. And so you can model these type of probabilistic methods using a quantum Monte Carlo method. And for some problems, the advantage is either quadratic in the minimum, exponential at best, particularly for a problem like this glued trees problem at the bottom here, which could maybe represent something where you have a very optically thick region of space that you're trying to get photons through. Another method is tensor networks. So this is sometimes called a quantum-inspired method because it's inspired by quantum many-body methods. And in this case, you're taking, you're compressing a very high-dimensional tensor, very high-dimensional operator into something that's more tractable both classically and quantumly. So this is compatible on classical hardware as well as quantum hardware and classical hardware. So specific significant speed and memory savings possible with this, depending on the structure of the problem. But this is a very promising research area for PDE solutions. Another one specifically for fluid flow problems, but also for general physics problems, is the Lattice-Boltzmann method. So this is an extension of cellular automata, where basically you have grid of space, and then the neighboring cells of a grid have rules that are have rules of how they are updated based off the center cell. So in this case, you're basically saying, okay, you have some behavior in this cell here, and then you you stream that solution to the neighboring cells, then you have some collision term that you then calculate. So it's actually very much a realization of the Boltzmann equation itself. There is a quantum version of it that carries its own advantages. And once again, this can run on classical hardware or quantum hardware. So this is a little bit what a Lattice-Boltzmann circuit would look like. And here's some example pictures of solving either porous flow or flow around a propeller. So Lattice-Boltzmann is another type of problem, that PDE that can be put on a quantum computer. And kind of the holy grail for a lot of things here is this HHL algorithm. So this is the first fault-tolerant quantum algorithm for solving general linear systems, so that AX equals B. This one's got an exponential speed up over classical linear solvers. But it comes with some fine print. You can't get the whole solution field out in one shot anyway. So you're limited to global characteristics of the problem, or maybe one grid point or something like that. And there's actually a very good article on Scott Aronson's website about specifically algorithms based off HHL, that there's a lot of what the challenges are in overcoming some of those limitations. And then finally, the variational methods. So this is sort of the NISQ regime that we're working in right now. And so variational quantum algorithms can solve properties of things like molecules and mid-sized quantum systems. So let's say you're trying to figure out the properties of trace gases in the atmosphere or things like that. There may be some use cases in this. Some PDE methods have been attempted, including a QSL project that I mentored earlier this year, where we solved the Poisson equation, or tried to solve the Poisson equation using a variational quantum algorithm. They do show some work or show some promise, but the implementation is challenging relative to the size of the problem. So typically in scientific computing and engineering, problems are very big. And quantum computers today are just really too small to get any large scale use out of for that type of problem. But what you can do is at least show the principle and show where the future research might lead. But some utility is possible for these larger, highly correlated systems, particularly related to like electronic structure and things like that. So that was sort of the overview of where quantum and AI fit into all this stuff. Discuss a little bit about where we think the future might be going here. So AI and machine learning methods are a pretty active and promising way of speeding up or otherwise improve scientific computations. And so there's lots of potential research avenues in this area. Particularly, I would say, if it were me, I would prefer methods that provide uncertainty estimates and physics constraints. That gives you a lot more confidence over the quality of your answer. Your implementation still requires careful analysis and verification. You have to make sure that you understand your bounds and capabilities fully when you're implementing stuff like this. But integrating it with existing simulators, because there are these big codes, remember, written in C++ and Fortran, integrating them is challenging because now you have to take something that was, say, written in PyTorch, and now it has to integrate with this Fortran code and has to be called very quickly many times in succession. So that's a challenging software engineering problem. On the side of quantum computing, there's still obviously still an open research stages for modeling and simulation of general PDEs. It's still very much an open research question of what this looks like in general on quantum computers. But there's obviously a very large economic incentive to do that. When you think about fluid dynamics problems specifically, the whole aerospace industry uses fluid dynamics. So quantum computing, being able to speed up those problems would be a game changer. Right now, the challenge, though, is that for quantum algorithms, the small output size compared to the state space is a challenge that has to be worked around very carefully, right? You get a very small input space right now. You get this exponentially huge state space to compute in, but then you collapse back down to a classical answer. So being able to work with that constraint is very important for figuring out how quantum computing will have an advantage for these types of calculations. So very much a wide open research field. And it's very much an area where I think there's lots of room for collaboration between AI and quantum experts, along with the domain experts who are doing these types of calculations. Domain expertise helps frame the problem realistically, so that way, the people developing the AI and quantum applications kind of have a sense of what makes sense, what doesn't. And at the same time, AI and quantum experts can help show the domain experts what's possible, and where the cutting edge, where the frontiers are. So what will you find in your application as you research this? And so here's a list of all the papers I showed here, and thank you.